very good morning to all of you. I am Chandrasekhar Vadlamani. Welcome to Tone Academy. From last 4 days, I think we are lecturing on chemistry for all the students who are actually writing their JEE, NEET, or the immediate exams which they wanted to focus on. You might be having several lectures online, but one thing I can say is please bank on us, because we will be following the sequence and you can just sit, relax, right? After your school or college, just relax and follow these, because each subtopic what we are dealing with will be linked with the JEE and NEET or any pre-engineering tests or pre-medical tests which you will be writing, right? I'm telling you convincingly that you need to bank. Please bank on us. Please bank on us, because we'll be doing the right thing which is important for your pre-engineering tests or pre-medical tests, right? And we are actually dealing with atomic structure, and in which from the last 4 days when we were lecturing, we started off with the Planck's quantum theory, and then we went for the applications of Planck's quantum theory, that is photoelectric effect, right? And taking a cue from the Planck's quantum theory is the Bohr's model, right? And let me actually brief something about yesterday's lecture, what we have done. If someone is joining us right now, for them, here is what we are doing in the previous lecture. Mind you, the very challenge before Bohr, was explaining the stability of the atom itself, right? Because there was a theory which states that, which was earlier prevailing, that the electrons around the nucleus, when they are actually moving around, they lose energy continuously and finally collapse into the nucleus, and atom as a whole collapses, right? There were absolutely no theories prevailing at that time to explain the stability of the atom before Bohr steps in. That's what we were telling yesterday. And I was clearly telling these things for you for a quick revision of what we have done earlier. Mind you that the very first postulate which fetched him Nobel Prize, and till now it prevails. You cannot substitute this postulate. There can be some drawbacks of Bohr, but remember that this postulate remains till date, and this is the postulate which has actually explains the stability of the atom. No one has done earlier. So, right, so he actually is proposing the non-radiating paths. I want everyone to actually go to the previous lecture and check it out. What exactly is an NRP? Is a non-radiating path, and as long as the electron is in the orbit, it's neither emitting energy nor losing energy. And let me tell you that this is designated by the principal quantum number, where n value starts from 1, 2, 3 and goes on, because the number of orbits in an atom is infinite, right? And n is not zero, ruling out the electron in the nucleus and hence explaining the stability of the atom. You must understand this, right? NRP. Synonymously, we call this to be stationary orbits, or I call this to be shells, and I call this to be orbits, and this is designated by the principal quantum number, right? And when you are actually suggesting that the total amount of energy remains constant for an orbit, because you're neither emitting energy nor losing energy. So the critical issue here is to address the stability of the atom. What Bohr has done is he's basically proposing the path in which the electron is revolving is neither radiating, neither emitting, nor what? Absorbing what? Energy. So if that is the case, then the energy of the orbit or the energy of the electron both mean the same. Both mean the same. Remember, electron is synonymous to orbit, electron is synonymous to shell, right? There is nothing like shell is different and electron is different. If there is no electron, no shell. That's how the thinking must be for a science student. You must understand that. So, as long as the electron is in the orbit, the energy of the orbit will be remaining constant. And if you just claim that it is constant and run away, people will ask you, how do you calculate it? For that, I gave you a volley of equations. And to calculate energy of the nth orbit, I think I have given you 13.6 by n square electron volts. That's yesterday I was telling you, right? There was also the second thing. So if someone is proposing non-radiating paths for electrons around the nucleus, then natural question arises that the electron in the shell, the path in which it is actually revolving, is neither emitting energy nor absorbing energy. The natural question arises, does light come out from the atom? That means that technically speaking, does atom radiate at all? Even though for a formality we are asking this question, does atom radiate at all? Of course it radiates because the spectrum is very much available. Spectrum is nothing but the impression of light made on the photographic plate. That means that when the light is actually coming out from the atom, that's the truth. That's the truth. The only thing left is we have to explain, in case when you propose non-radiating paths, where does the light come out from the atom, right? For that, Bohr has given explanations and is sticking to this word. He is sticking to this word that he proposes non-radiating paths. He is not deviating from that. Now the very question arises, how do you actually explain the spectra, the light coming out from the atom? That remains. For that, yesterday I was actually telling you that it is the transitions between my NRPs. It is the transitions between the NRPs is the reason for the light coming out. Assume that, you know, here is the nucleus, here is the first orbit, here is the second orbit. If this is the energy is constant because that is 13.6 electron volts and this is minus 3.5 electron volts, that is the first energy and that is the second orbit's energy. And if an electron wanted to shift from the second orbit to the first orbit, you cannot mix and bring all your energy which is there in you and mix it off with the first orbit. Because understand that you cannot do that because the energy of the first orbit must remain constant. You cannot gain energies like that, because energy of the orbit is fixed. That's what is non-radiating path is. So the only option left is when an electron from the second orbit wanted to jump into the first orbit, the only thing is the excess energy must be what? Vomited out, right? So when you're actually jumping out, the excess energy is given out, the light, and this is coming out in the form of spectra. And mind you, that is how the discontinuous spectra has been explained by Bohr. Rather, Bohr's theory is based on the Planck's quantum theory, because when his light is emitted, it is done in a discontinuous fashion in form of quanta, and that's how it is. And thereby the difference in energy, that is E2 minus H1, this is actually the vomit quantity. The vomit quantity of light, and which is actually given in the form of quanta. And when the difference in energy is delta E, energy has only one equation, that is h nu. That means again the energy is quantized. That means that it is shot out in the form of packets in a discontinuous fashion. That actually is giving you a discontinuous spectra. So two things has been explained by Bohr. Number one, he explained the very stability of the atom where earlier people could not even attempt it, right? And how did he do that? He proposed the non-radiating paths for electrons around the nucleus. That means that, simply speaking, the energy of the orbit remains what? Constant. The second thing is, if you wanted to explain the spectra, it's the transitions between the orbits which is the reason for the spectra. That's what the yesterday's discussion was. Now coming to today's discussion, I draw the attention of everyone. As I said, I was always telling you, what are you doing in atomic structure? In atomic structure, what you're doing is basically pinpointing the address of the electron, right? You need to pinpoint where the address of the electron is. You need to pinpoint it. There are several attempts made. First of all, as I told you synonymously, we were telling you what is the aim of this chapter is, you know, it's almost like you can draw an analogy that you wanted to write a letter to your friend on an envelope. And I think your writing is name, then door number, then the area, then the bigger area, that is which city he is from. Similarly, in atom also, people propose shells, which is a bigger area. That is proposed by Bohr. And when you wanted to get into the other part, that is a smaller area, that's nothing but the subshell. Subshell is proposed by Sommerfeld. So if you ask Bohr n number of times also, where is the address of the electron? If you ask Bohr, in his life he has only NRP, that's nothing but the shell or orbits or stationary orbits. Except for that, he doesn't know anything, because he's referring to a larger area, right? But our aim is to find out, pinpoint the address of the electron. So next comes Sommerfeld, right? He will be dealing with subshells. The next comes what? Lande, which he will actually tell you something about the orbitals, that is a much smaller pace. And then people will get into pinpointing the address of the electron, that Schrodinger's wave equation, where what is happening is you're actually almost 99%, 99.99% you're finding the probability of finding the electron. So basically what is happening is, from shell to the Schrodinger's wave equation, we are basically nothing but finding or pinpointing the address of the electron, you must understand. So in Bohr's theory, we are sticking to only shells, right? Now, let us actually see put in a sequence the postulates of Bohr, and here I am to the postulate number 3, and observe carefully, and I draw the attention of everyone now. And I draw the attention of everyone for today's lecture. Watch carefully here. When you actually go in for Bohr, the postulate number 1 is basically proposal. It is a proposal of NRP that we have discussed in detail yesterday. Second, it is transitions between NRPs. Is the reason for light coming out, is the reasons for spectra. This also we have done in detail, right? And the third one, what we wanted to tell now is observe carefully now. This is today's lecture, right? And when you actually open textbooks, your NCERT books or your 11th textbooks or any publishing reference book, then they say that in postulate number 3, something like this, I think you have done this, the angular momentum of an electron is a multiple of h by 2 pi. Is this the thing which is Bohr telling? No, absolutely not. Right? In his own wordings, if I can write the postulate number 3 for you, it is something different. The ones which is printed in your books are basically inferences that are taken out from what Bohr was telling. Right? And these things you can only know when you do the research, when you take up the research paper on it. Right? So remember, what Bohr was telling in the postulate number 3 is completely different, and what is printed in the textbook is an inference, right? In his own words, it's postulate number 3, which he is telling that my orbits, look into this. This statement has nothing to do with your 10th class, in your textbooks, what it is printed. It's completely different. He says that my orbits, my NRPs rather, my NRPs, those are nothing but what? Orbits. You can say synonymously they are orbits. My NRPs, and I draw the attention please. The my NRPs, my is so confident about his theory. He has done his homework. So my NRPs, the my non-radiating paths are, look into this what he is writing. He says they are privileged. They are privileged. This is postulate number 3, and I think you will be surprised that in any of the textbooks or the NCERT books or whatever, they don't write this postulate for you, right? The inference has been printed for you in the books. Now, what is it telling? He says that the my NRPs are privileged. They are privileged, right? So what I will do, I'll focus on the postulate number 3, why it is called privileged, and what is the inferences that are printed and what are the equations associated with it. Watch carefully here, and I just highlight the postulate number 3 of Bohr. Look into this. Look into this. Postulate 3. Postulate 3. And look into this. So proud he is. He says that my NRPs are nothing but what? For your understanding, I write orbits. Or even I can say are shells. Are shells. Remember that. My NRPs are privileged. They are privileged. Now what do you mean by that? That's postulate number 3 of Bohr. That's postulate number 3 of Bohr. I think you might be surprised in looking into the statement. These wordings which are given are exact wordings of Bohr when he was lecturing for his Nobel Prize some decades ago. Mind you, right? And my orbits are privileged. Now what do you mean by that? Let us explain this. Suppose when you say something is privileged, it's like this. For example, if you work for an Indian Airlines, right? And you can travel in Indian Airlines without ticket. I cannot travel because I don't work for Indian Airlines. So I can simply say the English statement being that, to travel in Indian Airlines, the fellow is privileged. The fellow is privileged traveling in Indian Airlines without ticket. So someone is traveling in Indian Airlines without ticket means that fellow seems to be privileged. He is a privileged person. And that privilege he got because he works for what? Indian Airlines. If you and me get without ticket, he will stop you at the gate itself, right? So you must understand that's what he means by privilege. Simply speaking, simply in simplest of the language possible, I can simply say that not everyone can travel in Indian Airlines without ticket. So similarly, he says that the my orbits are privileged. Privileged. That means that to travel, like for example, to travel in Indian Airlines, there is a condition. You travel in Indian Airlines without ticket, there is a condition. There is a condition. And the condition is you must work for it. Then you enjoy the privilege. Similarly, he says that my orbits are privileged. That means that I can simply say, when he say privileged, that means that not every electron can revolve in every NRP. Not every fellow can travel in Indian Airlines without ticket. Similarly, when you say that the NRPs are privileged, then it means that not every electron can revolve in what? Every NRP which he is proposing. And if I can simplify, what is the condition for you to travel in the plane? The condition seems to be you must be working for what? Indian Airlines. Similarly, if you say not every electron can revolve in every NRPs, that means that it implies basically he is setting a condition. He's basically setting a condition, right? Because you are privileged. Not every fellow can travel in every NRP. And let me tell you, you can also travel in his NRP, provided if you meet this condition. And look into this. He is setting a condition that's nothing but MVR is NH by 2 pi. Look into this. This is now someone is asking you when you're actually preparing for the exam or going through the textbook, if you come across MVR is equal to NH by 2 pi. MVR is equal to NH by 2 pi. Then remember this is actually the condition. This is actually the condition which is proposed for electrons to travel in NRPs. For the electrons to travel in NRPs. And NRPs are infinite. First, second, third, like that you have infinite NRPs. Each NRP, if you wanted to travel, a condition must be met. Right? Second, third, fourth, fifth, like that you have infinite number of orbits. Each one has a condition for electrons to travel. And let me tell you that suppose if the electron is not satisfying that condition, that electron is kicked out from the atom and stopped from entering into the constitution of the atom. You must understand this, right? Remember that. So not every electron, just like that, you can walk in and just revolve in an NRP. There is a condition, because after all, they are privileged. They are privileged. When they are privileged, then I think a condition must be satisfied. So back home, if someone is preparing for the exam and he or she or your brother and sister, they are actually mugging it out, the postulate of Bohr, then they are mugging in this fashion that MVR is equal to NH by 2 pi. That means the angular momentum, because in science, the product of mass, velocity and the radius is nothing but the angular momentum. It's a multiple of a constant, h by 2 pi. It's a multiple of a constant. You must understand. That's how they are mugging. Then when you hear someone mugging like that, you must stop them. You must stop them and tell them that this MVR is equal to NH by 2 pi, which you're mugging, is basically nothing but the condition for electrons to travel in a particular orbit proposed by shells. Not everyone can just walk in. It's not a walk-in. There is a condition. You must understand this. For example, if this is the nucleus, this is the first orbit, this is the second orbit, right? And the condition, if this is the first orbit, then the condition for traveling is MVR is equal to 1h by 2 pi. Now here n is 1. Here n is 1 because that's the first orbit. So if MVR is equal to h by 2 pi for any electron, right? Only those electrons where the angular momentum is equal to 1h by 2 pi, only those are allowed to travel in the first orbit. Remaining all orbits are kicked out of the atom and actually stopped from entering into the constitution of the atom, says Bohr. You must understand that, right? And if that is the case, if this is the second orbit, then MVR is equal to 2h by 2 pi. You must understand this, right? So it is 2h by 2 pi. You must understand. So if anyone wanted to travel in the second orbit, that condition must be met. That is, MVR is equal to 2h by 2 pi. And if anyone is not satisfying that condition, that electron is kicked out of the atom and stopped from entering into the constitution of the atom, says Bohr. You must understand this. So you just cannot walk in into, just because you have NRPs, you just cannot walk in into everything. So my understanding says, when you say such a thing, right? What is that you have done? Because you look into the postulates, it is something like this. I just read it out once again for my satisfaction. Look into this. My NRPs, that's nothing but the orbits or shells which I proposed, are privileged. When I say privileged, that means that not every electron can revolve in every NRP. That means basically you're setting a condition. Basically, you're setting a condition. And the condition is MVR is equal to NH by 2 pi, and N is an integer which is having a values 1, 2, 3 and up to infinity. So for the first orbit, this is the case. Second orbit, that is the case, right? That's what Bohr told. But even we have some reasonings. I think we should be doing that and actually see what exactly he means by this, right? Let us check. So not every electron can revolve in every orbit. You must understand this. So this is the basic things what Bohr was telling. Because we are also having some rational thinking. We should pull out some inference from this. And I draw the attention of everyone, what is the inference? Because remember, when we started atomic structure, the aim of the atomic structure is to pinpoint the address of the electron. Now I was telling you, whenever you ask Bohr a question, where is the electron? He will be telling you shell. If not, more specifically, he will tell you first shell, second shell, third shell. That's all. Now, how do we get that inference? Watch carefully here. My inference from this is like this. Watch carefully. Watch. This is what he meant. This is what he meant. Watch carefully. If you say, my NRP is privileged, that means that for electron to travel in the first orbit, the condition is MVR is equal to 1h by 2 pi. And for the second orbit, it's basically MVR is equal to 2h by 2 pi. And so on, and so on. If this is the case, what I understand and you must be understanding is, it is like this. Because you see the diagram here, if this is the first orbit and this is MVR is equal to 1h by 2 pi and this is MVR is equal to 2h by 2 pi. If this is the case, what I understand from what is in his mind, we can pull out an inference. The inference seems to be, the inference of the above postulates seem to be, it is like this. It is like this, that he, for the first time, I would like to underline this. He for the first time, trying to give address of electron. Wow. He is trying for the first time to give address of the electron. Well, I can justify this. What you do is you dial Bohr. And I ask, where is the electron? Then the first thing what he will tell is, it is there in the first orbit. It is there in the first orbit. Then if you say, no sir, the electron is not there in the first orbit, then the second thing what he will tell, it is in the second orbit. It is in the second orbit. If you don't find it in the first orbit, you will find it in the second orbit. If you say that no sir, the electron is not there in the second orbit, then he will ask you to go to the third orbit. If you say the electron is not there in the third orbit, then I think he is basically telling you that it is in the fourth orbit. Because his orbits which he proposed, the electrons must be satisfying a particular condition to revolve. Otherwise, you are kicked out of the atom and you are stopped from entering into the constitution of the atom. So, common sense says that where is the electron according to Bohr? Either it is in the first orbit, or it is in the second orbit, or it is in the third orbit. You must understand. That means that the electron in between these two orbits, the electron present in these two orbits is completely ruled out. Is completely ruled out. In between the orbits, the electron is completely ruled out. So what you're doing basically is, it's common sense, watch carefully, you're telling that a particular electron is in a particular area called shell, and you're ruling out a particular area. Implies that you are basically giving address of the electron, for example, if I wanted to find Lionel Messi of the footballer belonging to Argentina, then you must understand that the probability of finding Messi, 99%, will be in the football ground, not in a beauty parlor, of course. Similarly, he is basically telling that the probability of finding the electrons are in the NRPs, and in between NRPs, the electron's presence is completely ruled out. That's what his basic thing is. That means that I am actually underlining this. He for the first time, trying to give address of the electron. You must understand. That's why I am actually telling earlier also, what is the greatest merit of Bohr? If someone is asking, what is the greatest merit of Bohr? Well, the greatest merit of Bohr absolutely seemed to be the introduction of the principal quantum number itself, or the introduction of NRP itself. Because if you dial n number of times to Bohr also and ask for the address of the electron, in his life he has only NRP, shell, orbit. Other than that, he doesn't know anything, right? He simply will tell you where is the electron. The electron is in the shell. Because if it's not in the shell, you're not actually satisfying this particular condition, then you're kicked out from entering into the constitution of the atom. So you're ruling out some areas inside the atom where the electron is not present. Indirectly, you're actually telling you're giving address of the electron. That's what Bohr is actually proposing. Hope you understood that, right? And let's go in for the applications of Bohr's theory now, shall we? Yes. Now here are, we need to go in for the applications of Bohr's theory also. You cannot just put your postulates forward, but I think they must be even verified. They must be even verified, right? So for that, what people have done is basically, if you look into how do we go for its applications of Bohr's theory. Now this is basically applied to hydrogen atom. This is basically applied to hydrogen atom, right? And why hydrogen atom? Because remember that hydrogen has only one electron. So it is a singular electron system. You must understand. So this entire Bohr's postulate that you give a discontinuous spectra, the light is coming out because of the transitions, right? NRPs and all the postulates what you have actually proposed must be verified and must be applied to atoms. And firstly, I think he is applying it to hydrogen, which has one electron, and I call this to be single electron system, right? Single electron system. If you wanted to apply, how do we do this, right? What we do is, first of all, understand one point here. I call, and I am actually, hydrogen atom means I'm actually telling you about hydrogen spectrum. This I'm actually telling you about the hydrogen spectrum. Here are few highlights which I wanted to make it before I actually go for that. What is spectrum basically? What is spectra? What is spectra? Well, it's an impression. It's an impression. It's an impression made by light on a photographic plate. Or otherwise, people tell you that when the white light passes through the prism, it's splitting into several colors, and that's called spectrum. But I think in a smart way, if someone is asking you what is spectra, then I think it's an impression made by light on a photographic plate can be called as what? Spectra. You must understand that. Now if you look into this, atoms give basically discontinuous spectra. This is how the discontinuous spectra looks like. Discontinuous spectra. Now what is happening here? Suppose this is the first orbit, this is the second orbit, and when the electron from the second orbit is jumping to the first orbit, then the light is emitted. And the light is emitted and it is passed through a slit. This is how the slit looks like. In the spectrophotometer, you have a slit, and the light that is emitted by the atom is passed through the slit, and the slit image is actually having an impression like this. These are the lines what you get it, right? Understand that this is how the discontinuous spectra will be looking like. This is how the discontinuous spectra will be looking like. Understand carefully here, right? I'm explaining it to you again. So what is happening? The electron is in the second orbit and it is in the first orbit, and you wanted to now revolve in the second orbit to the first orbit. You have released some energy. This is the light which is emitted out from the atom that is passing through the spectrophotometer, and it has a slit image, and the slit image is coming out as a lines. And watch carefully here. I call some technical words, I'm using it here. Remember, in discontinuous spectra, what is one of the biggest features of discontinuous spectra? If someone is asking you, how do you actually define a discontinuous spectra? And first of all, understand that it is atoms. It is basically atoms that give discontinuous spectra. Mind you this, and I wanted to underline this. It is the atoms that give you discontinuous spectra, because molecules will give you a continuous spectra. Now, how do we actually distinguish a discontinuous spectra or the line spectra, what we call otherwise we call it to be line spectra, from a continuous spectra, which is otherwise called a band spectra. You must understand, how do we distinguish? Now look into this. As I said, the light that is given out from the atom is passing through the slit image of the spectrophotometer, and then you get lines like this. And when this is called the discontinuous spectra, now how do we define it? Is basically, if you look into these lines, these are basically well defined. These are called well defined lines. Now if you ask me, well, how do you define me? How do you define me? Well, I have a very distinguished features. My DNA is different from you and from anyone in the world, rather. I have very characteristic features. I have distinct features. So I'm well defined. Now what are the well defined parameters of me? My height, my eyes, my nose, or my DNA, my RNA, or whatever. These are completely different from anyone in the world. So I'm well defined person. Because if you have an identical twins, I think they are not well defined, you can simply say, right? When I say these are well defined lines, these are well defined lines, then understand that the parameters of this line, that is nothing but the wavelength or the frequency, are well defined. Well defined means they have a particular value. Mind you that, because when the light is given out due to the transitions between the NRPs, the light is nothing but a wave. The light is nothing but a wave, and wave will have a frequency or wavelength. You must understand. And the wavelengths are very much well defined. That means they have a particular value, and that value is very much different from the second line, and the value is very much different from the third line. You must understand this, right? So in discontinuous spectra, each line is very much well distinguished from the next line. You must understand. That is how the discontinuous spectra looks like. And I have seen many of the questions being asked in the exam. Atoms give what? Discontinuous spectra, or otherwise called line spectra. You must understand, each line is not merging with the other line. They are not like bands. Like, you see a rainbow outside. In rainbow, you can actually see a band. They are not well-defined line. They know violet merges with indigo, indigo merges with green, and they're looking like a band. Now here, that's not the case. And whenever light comes out from the atom, I think you will get well-defined lines on the photographic plate, well-defined lines on the photographic plate, and each line will be having a characteristic wave parameters on which they are defined. That means characteristic frequency, characteristic what? Wavelength, and I call this to be lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. You can get it because you have infinite number of non-radiating paths, so you get infinite number of lines. You must understand that, right? And watch. Now, very consciously I have done something. Very consciously I have done something. Look into this, the way I have drawn the discontinuous spectra, the way I have drawn it. Look into this. Now, this is the first line, right? There is a gap between the first line and the second line. Well, I want to redraw this again. Watch carefully. I am very consciously drawing this. So why did I draw like this? Watch carefully here. Watch. Now look into this. Let's apply this to hydrogen atom and come to the discontinuous spectra. So the basics of discontinuous spectra is the lines are well defined. They're not looking like a band. Each line has a definite, distinctive, clear word, wavelength and frequency. So those parameters are well defined. You must understand. Now coming to the applications of Bohr's theory, when I apply to hydrogen atom, this is how it looks like. First of all, we are dealing with atomic structure, right? So when you wanted to apply Bohr's theory to hydrogen atom, you want to apply Bohr's theory to hydrogen atom. But the reality is you don't have hydrogen atoms at all. You don't have hydrogen atoms. You have hydrogen molecules. You have hydrogen gas. When you take a sample of hydrogen gas, it consists of molecules. So where are the hydrogen atoms coming from? So what we are supposed to do, look into the sequence what we are doing. Now what I'm doing is I'm applying the Bohr's theory to hydrogen atoms. So what you do, you take a sample of gas. Watch carefully here. You take a sample of gas that is nothing but the hydrogen gas. You take a hydrogen gas because straight away you can't have an atom. And hydrogen atoms are so unstable, they readily combine giving you hydrogen gas. So you can't shop a hydrogen atom for sure. So you can shop hydrogen gas, and you know, when you take a sample of hydrogen gas, it will be containing molecules. Molecules of hydrogen. You have n number of hydrogen molecules, you must understand. But I think since we are dealing with hydrogen, with atomic structure, you must be converting that into hydrogen atoms. So what you do is expose this to thermal heat. You expose this to thermal heat, right? Heat. Then what happens is these hydrogen molecules, which is having a single bond, will be converting into hydrogen atoms. Remember that. So what I'm doing basically is I'm applying the Bohr's theory to hydrogen atom, right? But hydrogen atoms are not readily available. So what you're supposed to do is take the sample of what? Hydrogen gas, expose that to what? Thermal heat. Then the molecules break down to atoms. They break down to atoms. Atoms of hydrogen rather. They break down to the atoms of hydrogen. Then when you have n number of hydrogen molecules and each molecule is giving you 2 hydrogen atoms, then naturally you will have n number of hydrogen atoms now. Now, what is happening here? You have hydrogen atoms now. You have hydrogen atoms. Now, after breaking, you have broken the hydrogen molecules into hydrogen atoms. Now what is happening? All these, and I draw the attention, please. I draw the attention, please. Now watch carefully. We started off with hydrogen molecules. Now I have in my hand hydrogen atoms. And all these hydrogen atoms, all these hydrogen atoms absorb energy. All these will absorb energy. Mind you that you have n number of people, one in a room, I think you are absorbing energy in a different quantities. Similarly, all these hydrogen atoms absorb energy. And I was telling you always, when people absorb energy or emit energy, always done in the form of quanta, that's nothing but what? The Planck's quantum theory. If there are 2 bodies, one is emitting energy and the other is absorbing. And this will be done in form of quanta. That means you eat 1 packet, or otherwise you eat 2 packets, otherwise you eat 3 packets, or 1 photon, 2 photons, 3 photons, and not half photons. That never happens in science. That's what is Planck's quantum theory, because the energy is quantized. Right? So, if you have n number of hydrogen atoms, all will absorb energy. All these hydrogens absorb energy, but they do it in different quanta. That is h nu. Quanta is nothing but what? H nu. I was telling this in Planck's quantum theory, right? People will absorb it in 1 h nu, 2 h nu, 3 h nu, 4 h nu, n h nu, but they don't absorb it in half h nu. That never happens, right? So when you have infinite number of hydrogen atoms, each will be absorbing different quanta, and I can write it here. One will absorb 1 h nu, the other will absorb 2 h nu, the other will absorb 3 h nu, and it goes on. But the common thing is the number of hydrogen atoms that are available, all are absorbing what? Energies in different quanta. All are absorbing energies in different quanta. Now what will happen is, if someone is asking me like this, watch carefully, this is the language which you are supposed to use it as a science student. And watch, someone is asking me that this is a ground state atom. That's a ground state atom, right? And you have here an excited state atom. Ground state atom and an excited state atom. Someone asked me, what is the difference between a ground state atom and an excited state atom? Then I can simply say it is h nu, or simply quantum of energy. quantum of energy. Excited state atom has a higher energy compared to the ground state atom. You must understand. So don't tell several explanations for that. Be smart in your explaining. And if someone is asking you what is the difference between ground state atom and an excited state atom, I can simply say it is H nu. If he's questioning not H nu, then it is 2 H nu, 3 H nu, 4 H nu, and a ground state atom absorbing some quanta rises to excited state, and that's the difference between a ground state atom and an excited state atom. That's how you need to explain that. So if that is the case, I started off with hydrogen molecules. I exposed that to thermal heat. All the molecules have now reduced to hydrogen atoms, and all the hydrogen atoms are now eating energy. But the eating quantity is different. Right? They are eating energy. When they eat, then naturally you will rise to the excited state. Right? So simply what happens, all hydrogen atoms now excite. All the hydrogen atoms excite because people are eating energy. Right? The hydrogen atoms have eaten energy. Now excite. But to different excited states. Now, what do you mean by excited state? Technically speaking, hydrogen has only one electron, right? If hydrogen has one electron, look into this. This is the nucleus, this is the first orbit, and here is the electron in the ground state atom. That's the ground state of the hydrogen atom because the electron is in the first orbit and it's revolving in the first orbit. Now, what happens is, if you eat energy, now the electron is hit to the second energy level. Right? It is hit to the third energy level. It goes to the fourth energy level, fifth energy level. And it depends on which energy level with which the quantity of which the heat is absorbed or the energy is absorbed. But one thing is sure that all hydrogen atoms now excited to but to different excited states. Now I'm asking you, can you stay in excited state forever? You cannot stay in excited state forever. Right? Can you do work forever? No, absolutely not. Can you laugh forever? No. You need to come down to the ground state after some seconds. Similarly, what happens is, even though all the hydrogens have gone into an excited state, and within 10 power minus 8 seconds, now come on, have a feel of it. 10 power minus 8 seconds is almost, it's not even less than your blink of your eye. Mind you, all these hydrogens which have gone to the excited state, within 10 power minus 8 seconds, they basically de-excite. They de-excite. They are de-exciting now. Right? So they've gone to the excited state at different excited states and coming down now. Right? That is where I take a pause. Watch carefully here. Now I take a pause. Now what I will do is just go through this, what we were telling. I've taken a sample of hydrogen. What I'm doing is I'm applying the Bohr's theory to hydrogen atom. But atoms are not readily available. They are not readily available. So I've taken a sample of hydrogen gas, right? And I've exposed this to thermal heat. Then they are broken down to atoms. And all these atoms have eaten some energy in different quantities of energy. And they are rising to their excited state depending on the amount of heat they have taken. Right? But you can't stay for excited state forever, and you're coming down to the ground states, lower energy states. All the hydrogen atoms have risen to the excited state and they got de-excited. Watch here. This is the excited state they have gone into, right? Different excited states rather. And they are now de-exciting it. And the average time is 10 power minus 8 seconds. Now what I am interested, and I draw the attention of everyone. What I'm interested is, I'm interested only in, not in the excited state, different excited state where the electrons have gone. Now my entire focus is to which energy level they are de-exciting. Even though the electrons have risen to different excited states, say second, third, fourth, fifth, sixth, seventh, or anything, but I'm not interested to which excited state the electron has gone. I am now focusing on this bloody de-excitation process, which begins in an average time of 10 power minus 8 seconds. Right? I am interested in that. Then what happens, why I am interested in that? Because I am not interested in the excited state to which the electron is. I am interested in the de-excitation process. Because just assume in one atom, right? It has gone to the 7th energy level. And from the 7th, it can straight away jump to first in one of the atoms. Or the seventh, or in another atom, it has now risen to the seventh energy level, it might jump to the sixth. It's not everything, this excitation and de-excitation process is happening in infinite number of atoms, not in one atom. I'm not catching the hydrogen atom in my hands and looking for excitation and de-excitation. I'm not doing that. Infinite, so many number of hydrogen atoms are involved in the process of excitation and de-excitation. In one of the atoms, there is a direct jump from seventh to first. In one of the atoms, there is a jump from second to first. In some of the atoms, there is a jump from third to first. In one of the atoms, there is a jump from fourth to first. In one of the atoms, there is a jump from fourth to second. In one of the atoms, there is a jump from third to two. So what I'm doing, I'm surprised rather. Look into the keen observations, what people do, right? There is something in it, because normally simple things are ignored. And look into this, what people have done. They have forgotten about the excited state now, and they are focusing on the de-excitation process. What they have done is what they're doing is group all jumps to the first energy level. Forget about where it has gone. It might be going to 7, 6, 5, 4, 3. But to where it is jumping, the jump is to the first energy level. And I want to group that. And this is not happening in a single atom. It is happening in infinite number of atoms. Infinite number of atoms. So, all the jumps in different atoms, in several atoms of hydrogen are now grouped to the first energy level. So all the jumps to the first have been identified. Right? And the second, all jumps to the second energy level. Second energy level. And if someone is asking me, after second they will jump to first, no, because you need to come to the ground state. But the second to one has been now recorded in the first one. In the first one, right? All the jumps to second. Now what is second? 7 to 2. Like if I can write it specifically for you. It is like this. All jumps to 7 to 1, 6 to 1, 5 to 1, 4 to 1, 3 to 1, and even 2 to 1. All these are grouped. All these are grouped. You must understand. From where you are jumping is immaterial to me, to where you are, from where you are jumping is immaterial to me, to what level you are jumping, that I am grouping it. Now it's a common sense. Suppose in your classroom, they are grouping, they are segregating some people, or they are segregating into sections. There should be a basis. You just cannot segregate people just like that randomly. You come, I come, you go and sit in the classroom. There should be some basis. The basis must be a weekend exam or a grand test or something like that, or the height or the whatever, or the intelligence or whatever, or oratorship skills, whatever. There must be some basis for segregation. You must understand that. Similarly, when I am doing it from all these to the first energy level, I think there should be something common in them. There should be something common. That's why they have done it. Right? So to which excited state you have gone in is immaterial for me. To where you're jumping, I'm recording it because there is something common in this, and that I would like to reveal it. Similarly, what you do, all jumps to 2. It is 7 to 2. It is 6 to 2. It is 5 to 2. And it is 4 to 2. And this is 3 to 2. Mind you that. Now what people will ask me, what about 2 to 1? 2 to 1 has been recorded in the first one. Now someone is grouping all this, there should be something which is common in them. Similarly, I can simply say all the jumps to 3. Right? So I can simply say 7 to 3, or I can say 6 to 3, I can say 5 to 3, or 4 to 3. Because 3 to 2 has been recorded, and 3 to 1 has been also been recorded. You must understand that. Right? So that grouping, when I'm grouping that, I think there should be something common. That's why I have done it. I have not done it randomly without any basis for it. right? Similarly, all jumps to 4. Then it is 7 to 4, then it is 6 to 4, and then it is 5 to 4. Similarly, I can simply say, and all jumps to 5, then it is 7 to 5 and 6 to 5, and then all the jumps to the 5th energy level has been recorded. So now what is happening here? All this I have grouped for a purpose. There is something which is similar in all this, and mind you, when there is a jump, you're vomiting energy. So when there is a jump from 7 to 1, the light is emitted. The light is emitted. That's how it's coming out in the form of a spectra. That's what is hydrogen. That's what is Bohr's theory. You must understand, each jump what you're seeing here is giving out light with a specific lambda. And I have grouped it to which excited energy, so the excited states have been coming down to which energy level. Because I have grouped this, I have grouped that, I have grouped that, and I have grouped this and grouped that. And mind you, this is not happening in one atom. Many of the students I have seen, they think that it's happening in one atom. Absolutely not. You have n number of hydrogen atoms, and in all the hydrogen atoms, all these are taking place. This happens in one atom, this happens in another atom, that happened in another atom, that happened in another atom. Irrespective of that, all the fellows who are jumping to 1 in the several hydrogen atoms have been grouped, and the group is giving me a surprising information. It's giving me a surprising information, and that I will draw as a pictorial representation, and the energies, the light that is given out during all these transitions can be calculated, and what are the various equations concerning that and regarding Bohr, that I will deal in the next class. Right? And follow me, follow the Tone Academy. Please do subscribe. You can rely on us, you can bank on us rather, right? And whatever you're doing in your class and with your teachers is a separate thing. I think you can relax and listen to us and bank us as a last minute preparation for a better understanding. Here is Chandrasekhar Vadlamani signing off for you, and see you next class. Thank you very much.